The wall at 2. Seeing why a number keeps a secret. By Jonathan Kendall. RS a crack, ONOJK 123. N hands you the circle and keeps the angle. The factors are there, one caught, one shadowed, but the turn that finds them is the secret. Part 1. The asymmetry. Chapter 1. The wall. There is a wall running through the middle of the modern world, and almost no one who leans on it has ever seen it. It holds up the padlock that appears when you send a message, the number that moves when you buy something, the signature that says a piece of software is what it claims to be. It is not made of mathematics we understand. It is made of mathematics we merely trust, a gap we have never once proved is permanent, and have simply agreed to keep our weight on. The gap is easy to state, which is part of what makes its stubbornness so strange. Take two prime numbers, multiply them together. That multiplication is nothing. A child can do it. A machine can do it in the time it takes to say so, and the answer is a single larger number that carries no obvious trace of where it came from. Now try to run the operation backward. You are handed only the product, and ask to recover the two primes that made it. There is no known way to do this quickly when the numbers are large. Not because we have not tried, because for 50 years the best minds working on it have not found one. And the failure has been so consistent that we have built a civilization in the space it leaves behind. That is the whole of it. Multiplying is a walk downhill. Factoring, pulling the product back apart into its primes, is a climb up a cliff no one has found a path over. Everything else, the entire lock and key architecture that keeps the digital world standing, hangs from that one asymmetry. If someone found a fast way to factor, it would not be a breakthrough. It would be a collapse. I want to be honest, at the very start, about what kind of book this is, because the honesty is not a formality, it is the method. This is not a book that will teach you to break encryption. It could not. I do not know how, and neither does anyone else, and any book that claimed otherwise would be lying to you. Nor is it a cryptography manual, or a proof, or a new result waiting for a journal. It is something quieter and, I think, more useful. A sustained attempt to see the wall, to find out what shape it has, to ask not how do we get over it but the prior question almost nobody asks, why is it there at all? The distinction matters. The world is full of hard problems that are hard by accident, hard because we have not yet been clever enough. Those problems have the quality of a locked door whose key is simply misplaced. The factoring problem may be different. It may be hard the way a mountain is tall, not because we lack a ladder, but because the height is a real feature of the thing itself, built into its structure, not waiting to be dissolved by a better idea. This book is a long argument, made mostly through pictures, that the second possibility is the true one. That the difficulty of factoring is structural, that it lives in the numbers, not in us. I did not come to this through cryptography. I came to it through shape. For most of the people who study the factoring problem seriously, the terrain is algebraic and forbidding, a landscape of lattices and sieves and number fields, of algorithms whose names are longer than their inventors' patience. I respect that terrain and I am no master of it. What I have instead is a habit, maybe a stubborn one, of refusing to believe anything I cannot picture. When I meet a claim I cannot see, I do not trust that I understand it, no matter how many times I can recite it. So I build the picture first. Marbles on a number line, a triangle with two prime legs, a spiral that winds and then flattens, a clock that measures turning in a unit I had to invent, because the ordinary ones would not fit. Those pictures are the real content of this book, and they are not decoration laid over the mathematics after the fact. They came first. The claim that this book circles, the one it keeps recovering from new angles, chapter after chapter, arrived as an image before it ever arrived as a sentence. Here is the sentence, so you know where we are walking, even though it will not mean much yet. A number's magnitude and its factors are two readings that never reduce to one. A number has a size, how far along the line it sits, how much it counts, and a number has an inner structure, the primes it is secretly made of. These feel like they ought to be the same fact seen twice. Two windows into one room. The argument of this book is that they are not. They are two rooms, and the passage between them runs only one way. You can walk from the factors to the magnitude in an instant. That is just multiplication, but the magnitude does not remember the factors, does not point back toward them, gives you no angle of approach. The size is public, the structure is not, and the wall is exactly the width of the space between them. A word about temperament, because it governs everything that follows. The most tempting thing in the world, when you have built a beautiful picture, is to believe it has told you more than it has. A construction can be elegant, can click satisfyingly into place, can feel like a proof, and be worth nothing as one. I have felt that pull many times over the course of this work, and I have tried, each time, to resist it. When a construction turned out to explain nothing, I kept it in the notebook anyway, sitting honestly beside the ones that worked, because the dead ends are part of the map. When a picture teaches the right intuition, but would mislead you if you took it literally, I say so on the spot rather than letting the beauty carry you past the caveat. So you will find, threaded through this book, a recurring refusal. I will build something that looks like it might break the wall, and then I will show you exactly where it stores what you fed it and forges nothing new, where the crack you thought you saw is only the seam you brought with you. This is not false modesty. It is the point, an honest null result. No, the shape does not breach the wall either, and here is precisely why, is worth more than 100 overclaims, because it tells you something true about the wall's shape. Every failed attempt to get over it is a successful measurement of how tall it is. Here, then, is the road ahead. We begin on foot, at ground level, with the simplest possible question. Why does the wall stand where it does, at exactly two factors, and not one, and not many? That question has a clean geometric answer, and answering it will hand us our first tool. From there we will build the central construction of the book, a moving picture I call the rig, two primes launched up the axes as the legs of a triangle, the triangle blooming into circles, its very shape becoming a meter for how hard a number is to break. We will find the one place where that picture stops being only a picture and touches a real, deployed cryptosystem, where the geometry becomes, briefly and exactly, a working lock. Then we will follow the wall into stranger country, a second prime that the construction can see, but never stand on, present in the figure and absent from the integers. A public circle that hands you every possible answer while withholding the only one that matters. And finally, the deepest reframing of all, in which a prime stops being a place you travel to and becomes a leap you take, a toll you pay on a road that was infinite all along. By the end I will not have broken the wall. I will not even have proved it cannot be broken. That proof, if it exists, belongs to a future I cannot see from here. What I hope to have done is smaller and, I think, rarer, to have let you see the wall clearly enough that its permanence stops feeling like a lucky accident and starts feeling like what it may truly be, a fact about number itself, standing exactly where it must, at the width of the gap between what a number is and what it is made of. Let us go down to where the wall touches the ground, and start there. Chapter 2. Magnitude and Factors. Pick up a number, say the number 15, and turn it over in your hand. You will find that it answers to two different names, and that the two names do not know about each other. The first name is its magnitude. 15 is how far you have walked when you have taken 15 steps. It is a position on the line, a quantity, a height. This is the number as the world usually meets it, the number on the price tag, the number of people in the room, the reading on the dial. Magnitude is smooth and public and immediate. You can compare it to its neighbors at a glance. 15 sits just past 14 and just short of 16. And nothing about that ordering is hidden or hard. If I hand you two magnitudes, you can tell me instantly which is larger. The line is transparent. It keeps no secrets. The second name is its factorization. 15 is 3 times 5. It is the number you get when you set out 3 groups of 5, or 5 groups of 3, and it is only that, in exactly one way, because 3 and 5 are primes and cannot themselves be broken down further. This is the number's inner architecture, the private fact of what it is built from. And here is the strange thing that this whole book is an attempt to take seriously. The second name is not written anywhere on the first. We are so used to small numbers that the strangeness hides. 15 wears its factors on its sleeve. You saw the 3 and the 5 before I finished the sentence. So did I. That fluency is a trap, because it makes the two names feel like one name, like magnitude and factorization are just the front and back of a single coin you can flip at will. So let the number grow. Not enormously, just past the reach of instant recognition. Consider the number 3,317. Its magnitude you grasped as fast as you could read it. It sits a little past 3 1/3 thousand, comfortably between its neighbors, and if I gave you another 4-digit number you could rank the two without effort. The magnitude is as transparent as 15's was, but now tell me its factors. You cannot, not at a glance. You have to work. You start trying primes. Is it even? No. Divisible by 3. You check the digit sum. No. By 7. You divide and see. By 11, by 13, and you grind forward, candidate by candidate, until something finally goes in evenly. It is 31 times 107, as it happens, and I promise you did not see that coming, because there was nothing to see. The number gave no sign. The magnitude cost you nothing. The factorization cost you a search, and the number grew by only a few digits. That is the whole phenomenon, in miniature, sitting inside a number small enough to hold. Push the digits out to the length used in real cryptographic keys. Hundreds of digits, numbers longer than this paragraph, and the magnitude stays exactly as cheap as it ever was. Still just a position on the line. Still instantly comparable to any neighbor. But the factorization walks off past the edge of what every computer on Earth working together could finish before the sun burns out. The two names, which felt like one for 15, have come completely apart. One stayed free. The other became, for all practical purposes, unreachable. I want to name this asymmetry precisely because loose talk about it is where most confusion starts. It is not that factorization is unknowable. Every whole number has exactly one prime factorization. This is a theorem, old and certain, sometimes called the fundamental theorem of arithmetic, and it says the inner structure is always there, always unique, always waiting. 3,317 is 31 times 107, definitely and forever, whether or not anyone ever bothers to find it out. The factors are not missing. They are not undefined. They are simply not legible from the magnitude. The information is present in the number and absent from the number's face, and those are not the same thing. Nor is it that going the other direction is merely easier. It is a different kind of act entirely. To go from the factors to the magnitude, to multiply 31 by 107, is a procedure with a fixed number of steps. A mechanical grind that gets slightly longer as the numbers grow but never explodes. You turn a crank and the answer falls out. To go the other way is not a longer version of the same crank. There is no crank. There is only searching, trying possibilities, ruling them out, trying more, and the number of possibilities to try is what runs away from you. Multiplication is a road. Factoring is a wilderness with a treasure buried in it and no map. You can walk from the factors to the magnitude in an instant, but the magnitude does not remember the factors, does not point back toward them, gives you no angle of approach. This is the claim I set down at the end of the first chapter, and now it has a little more flesh on it. A number's magnitude and its factors are two readings that never reduce to one, not because we are not clever, we are very clever, and we have thrown centuries of cleverness at this, but because the two readings are genuinely, structurally different, and the passage between them runs one way. The forward direction is a fact you can compute. The backward direction is a secret you must find. Why should this be so? Here I have to be careful, because this is the exact point where a person wanting to write a triumphant book would start over claiming, and I would rather write an honest one. I do not know a proof that the backward direction must be hard. Nobody does. It is entirely possible, not likely, in the judgment of most people who study it, but possible, that tomorrow someone finds the crank that runs factoring backward as cheaply as multiplication runs it forward, and the wall simply falls, and this book becomes a curiosity about a difficulty that turned out to be an accident after all. I cannot rule that out. No one can. The permanence of the asymmetry is not a theorem. It is a 50-year failure to find the crank, hardened by use into something we lean our whole civilization against. But there is a difference between not being able to prove a wall is permanent and having no idea why it stands. This book lives in that difference, my wager, and it is a wager, offered as intuition and not as proof, is that the asymmetry is not an accident of our ignorance but a feature of the numbers themselves, that magnitude and factorization are two irreducibly separate readings, and that their separateness is something you can be brought to see, even if no one can yet prove it forces the difficulty. The rest of the book is the attempt to bring you to see it, not by algebra, I promised you shapes, and shapes you will get, but by building the two readings a body, giving magnitude a length and factorization an angle, and then showing you, over and over, how a figure can hand you the one while withholding the other. That is the move the whole book turns on, and it starts in earnest with the simplest question we can ask about the wall, not how tall it is, but where it stands. Why does a number secret live at exactly two factors, not one, not many, but two? That has a clean answer, and a geometric one, and it is where we go next. Chapter 3. Why the wall lives at 2. A line keeps no secret, a box keeps a poor one. To keep a good secret you need exactly two factors, and once you see why, you will never again think the number 2 in RSC is arbitrary. Start with one factor. A number with a single prime factor is a prime itself, or a prime raised to a power, and there is nothing to hide. Ask what 11 is made of, and the answer is 11. Ask what 27 is made of, and the answer is 3, 3, 3, all the way down. One prime repeated. There is no split to conceal because there is only one ingredient. A number like this is a line. It has length and nothing else, no width, no interior, no second dimension in which to tuck anything away. You can see straight through it. A line keeps no secret because a line has no inside. So we need at least two factors to have anything worth hiding, two ingredients, a genuine split, a number that was assembled from parts rather than standing alone. And now the temptation is to think that more parts would hide the secret better. If 2 primes make a good lock, surely 3 make a stronger one, and 10 make a vault. This is exactly wrong, and seeing why it is wrong is the key to the whole chapter. Picture the factors of a number as the side lengths of a shape. 2 factors give you a rectangle, a width and a height, and the number itself is the area. 3 factors give you a box, width, height, depth, and the number is the volume. 10 factors give you a shape in 10 dimensions, if you can stand to imagine it. The number, the area, the volume, the hypervolume, is public. It is the magnitude, the thing anyone can read. What is hidden is the particular side lengths that produce it. The question is, given the area, how hard is it to recover the sides? Here is the thing people's intuition gets backwards. When you have many factors, you have many small ones. A number that splits into 10 primes is, on average, built from 10 little primes, and little primes are easy to find. You trial divide by 2, by 3, by 5, and they come tumbling out one after another, because a small factor is a shallow hiding place. The more factors a number has, the smaller they tend to be, and the smaller they are, the faster a simple search rakes them in. A 10-dimensional box does not hide its sides better than a rectangle. It hides them worse, because every one of those 10 sides is short, and short sides are found by the crudest search there is. Strength, then, is not spread. Strength is concentration. The hardest number to pull apart is not the one with the most factors, but the one with the fewest that still has a split to hide, 2, and whose 2 factors are pushed as large as they can go for a number of that size. Two big primes and nothing else. All of the numbers magnitude poured into just two ingredients, each of them huge, neither of them a shallow catch for a trial dividing search. That is a semiprime, a product of exactly two primes. And that is what real cryptography uses, not by accident but for precisely this reason. The wall is strongest at two factors because two is where you can force both of them to be large. A line keeps no secret. A box keeps a poor one. Strength is concentration, not spread, and the wall stands at exactly two factors. Let me make the geometry sharper, because there is a second, more beautiful reason two is special, and it will set up everything in part two. Give the two factors of a semiprime to a triangle. Let one prime be the length of the horizontal leg and the other prime the length of the vertical leg, meeting at a right angle. The two primes are the legs. The long diagonal that closes them off is the hypotenuse, and the area enclosed, half the base times the height, is half the product of the two primes, half the semiprime. The public number is written in the area. The secret split is written in the two legs. One shape, holding both readings at once. Magnitude as the space enclosed, factorization as the particular pair of edges that enclose it. Now watch what the shape of that triangle tells you. If the two primes are wildly unequal, a tiny one and a huge one, the way most numbers are built, the triangle is a long thin sliver, almost flat, one leg stretched out and the other barely lifted off it, and a sliver is easy to read. The short leg is right there, small and obvious, a shallow hiding place found by the crudest search. But if the two primes are close to equal, both large, both comparable, neither one a giveaway, the triangle is fat and balanced, tall as it is wide, and there is no short leg to grab, no shallow catch, nothing the crude search can rake in. The shape of the triangle is a picture of the difficulty. Thin means weak, fat and balanced means strong. This is the seed of the entire construction to come, and I want you to hold the image before we build the machine around it. A right triangle whose two legs are the secret primes, whose area is the public number, and whose proportions, how balanced or how lopsided it is, are a difficulty meter you can read with your eye. A clock built from prime-edge triangles, ticking through the numbers, showing you at a glance which ones keep their secret and which ones give it away. So the wall lives at two for reasons that are both arithmetic and geometric, and the two reasons are the same reason seen twice. Arithmetically, 2 is the fewest factors that still hides a split, and it is the only count that lets you force both factors to be large, and largeness is what defeats the crude search. Geometrically, 2 factors make a triangle, and a triangle has a shape, and the shape can be balanced in a way that a line cannot. A line is all length and no proportion, but a triangle can be made square on and stubborn, hiding its legs in plain sight by making neither one short. One factor is a line, and keeps no secret. Many factors are a box of short sides, and keep a poor one. 2 large factors are a balanced triangle, the one shape with an interior deep enough to hide and no short edge to give it away. The whole modern lock is built on that single choice of number, and the choice is not arbitrary. It is the only place the wall could possibly stand. We have our tool now, the triangle whose legs are the primes and whose shape is the difficulty. In the next part we set it in motion. We launch it up the axis, let it grow, and watch it bloom into circles, and the still picture becomes the rig. Part 2. The construction. Chapter 4. 2 rockets up the axis. Everything until now has been a still photograph, a triangle, frozen, its 2 prime legs holding a secret in the area between them. It is time to set it moving, because a number is not really a static thing, it is a place you arrive at by counting, and counting is motion. Let me show you the machine I have been building toward, the one I call the rig, and let me build it the way it was actually built, from 2 blocks, climbing. Put down 2 axes, the way you would to draw any graph, one running east along the floor, one running north up the wall, On each axis, place a clock, not a clock that measures seconds, but a clock that measures primes. It ticks, and with each tick it advances not by one but to the next prime in line. 2, then 3, then 5, then 7, 11, 13, and on. The horizontal clock climbs east along its axis, notching off one prime at a time. The vertical clock climbs north up its axis, doing the same. 2 rockets rising, each leaving a vapor trail of primes behind it, each pausing at the primes and skipping everything between. Now stretch a triangle between the 2 rising tips. At any moment, the horizontal rocket is at some prime. Call its height along the floor P, and the vertical rocket is at some prime. Call its height up the wall Q. Drop a leg from each. The horizontal leg has length P, the vertical leg has length Q. They meet at the corner where the axes cross, and the long diagonal closes them into a right triangle. This is the same triangle from the last chapter, the one whose legs are 2 primes, but now it is alive, its legs lengthening and shifting as the 2 rockets climb. The area of that triangle is half the base times the height, half of P times Q, half a semiprime, and the semiprime itself, the full product P times Q, is the public number, the one anyone is allowed to see. The 2 legs are the private split that produced it, so the moving triangle carries, at every instant, exactly the 2 readings this book keeps circling, the magnitude, poured into the area it encloses, and the factorization, standing plainly in the 2 legs that enclose it. The rig is the 2 readings given a body and set in motion. Watch what happens to the triangle's shape as the rockets climb, because the shape is where the meaning lies. Suppose the 2 rockets climb at the same thrust. Suppose P and Q stay close to each other, both advancing through comparable primes. Then the triangle stays balanced, as tall as it is wide, its right angle looking square and stubborn, the whole figure fat and stable. This is the strong number from the last chapter, the balanced semiprime, the one with no short leg to give it away, but let one rocket outrun the other. Let P shoot far ahead while Q lags near the floor, and the triangle leans, shears, collapses toward a thin sliver stretched out under the fast rocket. That is the weak number, the lopsided one, the one whose small factor is right there for the taking. The rig does not just carry the 2 readings, it shows you the difficulty in its posture, standing square for the strong numbers and keeling over into a sliver for the weak ones. And then the triangle blooms. Here is the move that turns a diagram into the rig proper, and it is worth slowing down for. Take each leg of the triangle and let it swing. Let it be the radius of a circle, spinning out a full round from the corner where the axes meet. The horizontal leg P sweeps out one circle, the vertical leg Q sweeps out another. Where the 2 circles overlap they make the shape the old geometers called a vesica, a pointed almond of doubled space, the lens where 2 equal circles cross. The triangle, which was a taut still thing, opens into a flower of overlapping circles, 1 bloom per leg. When the legs are equal, the balanced, strong case, the 2 circles are equal and the bloom is round and symmetric, a clean 4-petaled flower. When one leg outruns the other, the circles are mismatched and the bloom shears lopsided, drag toward the faster rocket. The same information, balanced versus lopsided, strong versus weak, is now written 3 ways at once, in the height of the 2 rockets, in the posture of the triangle, and in the symmetry of the bloom. The rig says the same true thing in 3 languages, so that whichever one your eye is fluent in, you can read it. 2 prime rockets climb the axes. The triangle stretches between them and its circles bloom. Equal thrust, round balanced bloom. Unequal, and it shears toward the faster rocket. And it breathes, because the primes do not come evenly. There are wide gaps and sudden clusters, the famously jagged meter of the prime numbers. The whole rig pulses irregularly as it climbs, stretching and easing in the ragged rhythm of the prime gaps, never settling into a steady beat. It is not a metronome. It is something more like a heartbeat under exertion, quick here, held there, always uneven, and the unevenness is not noise. It is the prime numbers themselves, showing you their spacing through the motion of a machine. That is the rig, assembled, two clocks that tick in primes, a triangle stretched taut between their rising tips, its area, a public semiprime, and its legs, the private factors, a posture that stands square for strong numbers and shears flat for weak ones, a bloom of vesica circles that echoes the same balance a third time, and over all of it the uneven breath of the prime gaps. Right now it is running free, the rockets climbing through the primes in order, showing us the space of possible semiprimes and what strength looks like across it. That is beautiful, but it is a survey, not yet an interrogation. In the next chapter we stop letting the rockets run free and start feeding the rig the real thing, the actual factor pairs of one semiprime after another, making the machine tick through genuine numbers and letting its shape become, beat by beat, a mirror for how hard each one would truly be to break. Chapter 5. The shape is the difficulty. In the last chapter the rockets ran free, climbing through the primes in order, surveying the whole open country of what a semiprime could be. That was a map of the possible. Now I want to stop surveying and start interrogating, to point the rig at real numbers, one after another, and let it tell me how hard each one would truly be to break. So change how the machine ticks. Instead of letting the two rockets climb freely through the primes, feed the rig a list, the actual semiprimes, in order, each with its one true factor pair. 6 is 2 times 3, 10 is 2 times 5, 15 is 3 times 5, 21 is 3 times 7, 35 is 5 times 7. On each beat, the rig sets its two legs to the real factors of the next number on the list, not a free choice of primes, but the specific pair that genuinely multiplies to make that number, and then we watch the triangle it builds. What you see, once the list gets going, is mostly slivers. This surprises people, and it is worth sitting with. Most semiprimes are lopsided. Reach into the numbers at random and the semiprimes you pull out will nearly all have one small factor and one large one, because small primes are common and get used constantly, while the balanced pairings, two large comparable primes multiplied together, are rare and thinly scattered. So the rig, ticking through the real numbers, spends most of its time throwing thin sheared triangles, a long leg stretched out under a fast rocket, a stubby leg barely lifted off the floor, the whole figure flat and lopsided and, as we'd established in Chapter 3, easy. A thin triangle has a short leg, and a short leg is a shallow hiding place, raked in by the crudest trial-dividing search, sliver after sliver after sliver, most of the number line, weak by construction. And then, rarely, the triangle snaps fat. Every so often the list hands the rig a number whose two prime factors are close to equal, both large, both comparable, neither one a giveaway, and the triangle, which had been lying flat, stands suddenly upright, tall as it is wide, its right angle square and stubborn, its vesica bloom opening round and symmetric. These are the balanced semiprimes, the strong numbers, the hard ones. There is no short leg to grab, nothing for the crude search to catch. The whole magnitude of the number is poured into two large ingredients and neither one leaks. When the rig hits one of these, the round bloom is a warning light. This one keeps its secret. Each tick lays out a real factorization as its triangle. Thin and gray means lopsided, easy. Fat and round means balanced, strong, the hard-to-factor semiprimes. Step back and let the whole sequence run, and it becomes a landscape. A long, low plane of thin gray slivers, the weak, lopsided majority, interrupted here and there, at the rare balanced semiprimes, by a fat red bloom standing up out of the flatness like a landmark. The difficulty of factoring, which is an abstract and forbidding thing, an asymptotic statement about search costs, has become a terrain you can walk your eye across. You can see where the hard numbers are. They are the tall, round blooms, and they fall exactly where the two primes run close together, and they are sparse, and between them stretch long runs of easy sheared slivers. The shape is the difficulty. That is not a metaphor I am decorating the mathematics with. It is the literal content. The proportion of the triangle is the balance of the factors, and the balance of the factors is the hardness of the number, so the triangle's proportion and the number's hardness are the same fact wearing two faces. Why does this matter, beyond being a pretty way to sort numbers? Because it tells you what a strong key looks like, and it lets you feel, rather than merely accept, why the strong ones are strong. When someone chooses a number to build a real lock from, they are not reaching in at random. If they did, they would almost certainly grab a sliver, a lopsided number with a small factor, and their lock would fall to the first trial dividing search that walked past. They are deliberately hunting the rare fat blooms, two large comparable primes, multiplied into a number whose triangle stands square, whose factors are both buried deep, whose secret does not leak from a short leg. The whole art of picking a key is the art of finding a round bloom in a field of slivers. And the rig lets you see that art. It lets you see that strength is not something added to a number from outside, not a coat of armor bolted on, but a property of its internal proportions, how balanced its two factors are, how square its triangle stands, how round its bloom opens. A weak number and a strong number are built the same way, out of two primes, by the same multiplication. The only difference is the balance, and the balance is visible. And once you have seen the landscape of slivers and blooms, you will never again think of hardness as an abstract property. It is a shape, you can point at it. But here I have to slow you down, because the intuition I have just given you is almost right, and almost right is exactly where careful thinking goes to die. You now believe, correctly, that strong numbers are the fat balanced blooms and weak numbers are the thin slivers. So the natural next thought, the one your mind is forming right now, is that the fatter the bloom, the stronger the number, and that the ideal key would be the very roundest triangle of all, the two primes as close to equal as they can possibly get. That thought is wrong, and it is wrong in a way that actually matters, in a way that could weaken a real lock. The fattest blooms are not the strongest. Some of them are as weak, in their own way, as the slivers. Understanding exactly why is the whole of the next chapter, and it is the most important caveat in the book, the place where a beautiful picture, taken one step too literally, would lead you straight into a trap. Chapter 6. An honest note on picking keys. The last chapter left you with a rule that is 9/10 correct and 1/10 dangerous. Fat balanced blooms are strong, thin slivers are weak. Hunt the round ones. The 9/10 is real. The dangerous 10th is that the very roundest blooms, the two primes pressed as close to equal as they will go, are not the strongest at all. They are weak by a different door. This chapter is about that door, and about why no picture in this book, however beautiful, should ever be used to make a real key. Here is the trap. Suppose you take the rule too literally and reach for maximum roundness. You pick two primes that are almost touching, as near to each other as two distinct primes can be. Your triangle stands perfectly square. Your bloom is as round as a bloom can get. By the intuition of the last chapter, this should be the strongest lock imaginable. It is one of the weakest, and the reason is old and simple. When the two primes sit very close together, the number they make sits very close to a perfect square, the square of whatever value falls between them. And there is a factoring method, older than modern cryptography by centuries, that does nothing but walk outward from the nearest square root, testing as it goes. Against a lopsided number this method is hopeless. The factors are nowhere near the square root and the walk would take forever. But against two nearly touching primes, the factors are sitting right beside the square root, a step or two away, and the method finds them almost immediately. The roundest bloom is the one whose factors huddle closest to the square root, and huddling near the square root is precisely the vulnerability this ancient walk exploits. Maximum roundness is not maximum strength. It is a second kind of weakness, hidden inside the very feature that looked like strength. The very fattest blooms are also weak, crackable by a method that walks outward from the square root. The true target is balanced but not adjacent. So the real target is a narrower thing than the last chapter implied. Not the thinnest slivers, those fall to trial division. A small factor raked in from below. Not the roundest blooms, those fall to the square root walk, two factors caught huddling at the center. The strong keys live in a band between the two failures. balanced, but not adjacent. Two primes large enough and comparable enough that no short leg leaks from below, but far enough apart that they do not both sit in the shadow of the square root and get swept up from the middle. Strength is not the extreme of balance. It is a disciplined interior, away from both edges, away from the sliver and away from the perfect square alike. You can see it in the rig if you know to look. The safe zone is not the flattest triangle and not the most perfectly square one, but the well-proportioned one that stands solidly upright without straining toward a perfect equality of legs. There is a whole geometry to that safe band, a region on the landscape of plumes that is neither the low plane of slivers nor the razor's edge of the perfect square, and mapping it precisely is a real and subtle thing. The picture teaches the shape of the safe zone. It teaches which way is danger on either side. What it does not do, and must never be trusted to do, is hand you a specific number to lock your door with. I want to be very plain about this, because it is the ethical spine of the whole project, and I would rather say it too loudly than too softly. No picture in this book should ever generate a real cryptographic key. Not the rig, not the bloom, not the difficulty landscape, none of it. Choosing a key that will actually guard something is not a matter of finding a nicely proportioned triangle. It requires two things this book cannot give you. First, vetted software, code written and reviewed and hardened by people who do this for a living, that knows about the square root walk and a dozen other attacks subtler than anything I have drawn here, and that steers away from all of them automatically. Second, and just as important, it requires cryptographically secure randomness, a source of unpredictability good enough that no one can guess or reconstruct the choices you made. A key that is balanced but not adjacent but chosen predictably is no key at all. An attacker who can retrace your reasoning does not need to factor anything. The rig teaches you the shape of strength. It cannot supply the randomness that strength also requires, and it does not know the attacks that a real generator must dodge. The rig teaches the shape of strength. It is not a tool for forging it. No picture should generate a real key that needs vetted software and cryptographically secure randomness. This chapter is short, and it interrupts the momentum of the construction on purpose. It would have been easy to leave it out, to let you walk away from chapter 5 believing that rounder is stronger, full stop, and enjoying the tidy picture. That would have been a more satisfying book and a less honest one. The whole method of this project is to build a picture until it clicks, and then, the moment the click tempts you to trust the picture further than it has earned, to stop and say exactly where it stops being true. Here the picture stops at the edge of key generation. It shows you the terrain, slivers below, the square root cliff above, the safe band between, and that terrain is real and worth seeing. But a map of where the strong numbers lie is not a machine for minting them, and I will not pretend it is. With that boundary marked, we can go on to the strangest and most important turn in the book, the one place where the rig stops being only a way of seeing and touches a real, deployed lock, exactly and provably. That is the hinge, and it is where we go next. Part 3. The hinge. Chapter 7. Where the rig is really a lock. Up to now I have been scrupulous, almost to a fault, about calling the rig a picture, a way of seating, an intuition machine. I have warned you off treating it as a proof, off trusting it to make a key, off mistaking its beauty for authority. That scrupulousness was earned and I stand by it. But this chapter is the exception the caution was protecting, because here, at exactly one hinge in the whole construction, the picture stops being only a picture and becomes a real, deployed cryptosystem, precisely and provably, not an analogy to one. 1. Take the two legs of the rig's triangle, the two primes, P and Q. We have been forming their product to get the public number, n equals P times Q. That number n is the semiprime, the magnitude, the thing anyone may see while the two legs stay secret. So far, so familiar. Now add a single new move and watch a lock appear out of nothing. Take any number you like, call it x, square it, and wrap the result around n, keeping only the remainder after you divide by n. In the notation of arithmetic, that wrap around and keep the remainder is written mod n, and the whole operation is x maps to x squared mod n. That is it. Square a number. Take the remainder modulo n. This little operation has a name. It is called the Rabin function, after the cryptographer who studied it, and it is a genuine one-way lock, easy to walk forward. Squaring and taking a remainder is cheap, a crank you turn without effort, hard to walk back, given only the wrapped-around result. Recovering the x that produced it is, for a well-chosen n, a wall. And now the sentence this whole book has been walking toward, the one that justifies every page of the caution that came before it. The hardness of that lock is not like the hardness of factoring. It is not related to it, not reminiscent of it. It is provably equal to it. There is a theorem, a real one, with a real proof, not an intuition of mine, that says, if you could reliably undo the Rabin function, walk it backward, recover its inputs, then you could factor n. And if you could factor n, you could undo the Rabin function. The two abilities stand or fall together. Breaking this lock and splitting this number are, in the precise sense the theorem makes precise, the same act. This is rarer than it sounds. Most cryptosystems only lean on factoring. They are believed to be hard, and their exact relationship to the factoring problem is a matter of conjecture and hope. The Rabin function is bolted to factoring by proof. Its wall and the factoring wall are the same wall. Square any number and wrap it around n, and you have the Rabin function, a genuine one-way lock whose hardness is provably equal to factoring. This is why the rig is not merely decorative, and I want to make the stakes of that clear before we go further. If the rig were only a pretty way to sort semiprimes into strong and weak, it would be a nice teaching aid and nothing more, a diagram that lives entirely on my side of the glass, touching no real system. But the rig is built from exactly the ingredients the Rabin lock is built from. 2 primes as legs, their product as the public modulus. The very same, and that is half the area of the rig's triangle is the n you wrap the squaring around. The construction and the cryptosystem are not neighbors. They are the same object, drawn in 2 notations, one geometric, one arithmetic, and the theorem about the Rabin function is therefore a theorem about the rig. When the rig shows you a fat balanced bloom and says this number keeps it secret, it is telling you something true about a real lock, because the number in the bloom is the number in the lock. That changes the status of everything the rig has shown us. The difficulty landscape of the last chapters, the plain of slivers, the rare red blooms, the safe band between the trial division floor and the square root cliff, is not a landscape of a made-up game. It is a landscape of Rabin locks, of real one-way functions, of walls provably as tall as the factoring wall itself. The picture has been touching the real system all along. This chapter is just where I finally admit it, having spent the earlier chapters earning the right to be believed. But a lock is only half a cryptosystem. A one-way function you can never read open is not a lock at all. It is a grave. Whatever you seal with it is lost even to you. A real lock has a trapdoor, a secret that lets exactly one person walk the one-way function backward while everyone else stands at the wall. The Rabin function has such a trapdoor, and here is the part that still astonishes me every time I return to it. The trapdoor is already in the rig. It is not a new piece of machinery we have to bolt on. It is a move the triangle can already make, a swing it was always capable of, sitting in plain sight in the geometry we have had since chapter 4. To find it we have to look at what the bloom's really doing, its four-fold symmetry, the 4 petals of the round flower, and at the single hinge move that stands a flattened triangle back up. Those 2 things, the 4-fold bloom and the hinge, turn out to be the 2 halves of the Rabin trapdoor, written in geometry. That is the next chapter, and it is the keystone of the whole book, the place where the secret that unmultiplies the number is revealed to be the same motion as the hinge that unflattens the triangle. Same move, 2 languages. Chapter 8. 4 roots. One trapdoor. This is the keystone. Everything before it was building toward this claim, and everything after it flows from it. The secret that unmultiplies the number is the same motion as the hinge that unflattens the triangle. Same move, 2 languages. Let me build it slowly, because it is the single most important thing the rig has to say. Recall the lock from the last chapter. Square a number, wrap it around n. Now ask the question that makes a lock a lock. How do you walk it backward? You are handed a wrapped around square and asked for a number that produces it. In ordinary arithmetic, off the number line, a positive number has exactly 2 square roots, one positive and one negative, mirror images across 0. That is the familiar fact. The square root is 2-valued, plus and minus. But we are not on the ordinary number line. We are working modulo n, wrapped around a semiprime that is the product of 2 primes. And here something quietly remarkable happens, because n is built from 2 separate primes. The wrapped around world it defines is secretly 2 worlds stitched together, one belonging to P, one belonging to Q, and a square root has to be a square root in each of them at once. Each world contributes its own plus or minus choice, its own mirror pair. 2 independent binary choices, made together, give not 2 answers but 4. In the world modulo a semiprime, a square typically has 4 square roots, not 2. 4. Hold that number, and now look back at the bloom. The rig's bloom, when the triangle is balanced, opens into a 4-fold symmetric flower, 4 petals, 4 quarters, a shape with exactly the symmetry of a thing that can be reflected 2 independent ways. I did not design it to have 4 petals to match the 4 roots. It has 4 petals because that is what 2 overlapping circles swung from perpendicular legs do. The geometry produces the 4-fold symmetry on its own, for its own reasons. And when I first set the 4 petals of the bloom beside the 4 roots of the Rabin lock, they were the same 4. The 4-fold symmetry of the bloom is the 4 square roots the lock always has. The geometry had been drawing the structure of the cryptosystem before I knew to look for it. The 4-fold symmetry of the bloom is the 4 square roots the lock always has. This is the first half of the trapdoor, and it is already strange enough to sit with. The 4 petals are not decoration and not coincidence. They are the 4 roots, the 4 pre-images any wrapped around square has, laid out in space, the 2 independent mirror choices of the 2 hidden primes made visible as the 2 independent symmetries of a flower. Now the second half, and the one that turns a curiosity into a key. Suppose you are handed not one of those 4 roots but 2 of them, and not a mirror pair, not a root and its own negative, but 2 roots that came from different choices in the 2 hidden worlds, 2 roots that agree in one prime's world and disagree in the other's. When you have such a pair, something almost magical falls out. The difference between them shares a factor with n but is not all of n, and so a single, cheap, ancient operation, taking the greatest common divisor, the largest number that divides both, a computation older than algebra and faster than almost anything, splits n cleanly back into p and q, 2 of the 4 roots, one greatest common divisor, and the wall falls. The secret spills, the number unmultiplies. That is the trapdoor of the Rabin lock, stated arithmetically, and now watch it become geometry. Go back to the rig and find the move I have been calling the hinge. Through the earlier chapters we let the triangle flatten, shear toward a sliver, collapse toward the axis, lie down flat. The hinge is the opposite motion, the move that pins one vertex in place and swings the flattened triangle back up, standing it upright again, opening the interior that flattening had closed. Swing one leg out into its circle and bring it back to standing. It is a single, definite motion, the geometric act of uncollapsing. Here is the keystone. That hinge, the swing that stands the flattened triangle up, is exactly the trapdoor move. Given 2 of the 4 roots, 2 of the 4 petals of the bloom, the greatest common divisor that splits n is the arithmetic shadow of the hinge that unflattens the triangle. To have 2 suitable roots is to have the leverage to stand the triangle up. To stand the triangle up is to split the number. The move that unflattens the shape and the move that unmultiplies the number are one move, seen in two languages, geometry saying it with a swing, arithmetic saying it with a divisor. The rig builds the key, the squaring is the lock, and the hinge is the trapdoor, the move that stands the flat thing up, available only to whoever kept the two legs. Step back and see the whole machine as one honest picture of one real system, every part now accounted for. Choosing two balanced primes, hunting the fat red bloom in the field of slivers, is key generation. That was part 2. Flattening those two legs into a single public number, the product n, is forming the modulus, the public magnitude everyone is allowed to see. Squaring any number and wrapping it around that modulus is the lock, the Rabin one-way function from the last chapter, and the hinge. Swing one leg into its circle and back. Stand the flattened triangle up. Is the private trapdoor, the move that reopens what the lock closed. Available only to whoever kept the two legs to begin with. 4 parts of a criticisystem, 4 parts of the rig, and they are the same 4 parts. The thing I keep returning to, the thing that made me trust the rig was more than a pretty diagram, is this. The secret was never the number. N is public. Anyone can have it. The secret was always the two legs, the two primes that made n, and the hinge that remembers them, the one motion that can stand the flattened figure back up, because it never forgot which two legs were folded down to make it. Whoever kept the legs kept the hinge. Whoever kept the hinge can reopen the lock. Everyone else has only the flat, public number and a circle of possibilities, and no way to stand the triangle up. That circle of possibilities, what n looks like when you have thrown the legs away and kept only the public number, is where the book turns next, into its 4th part, the shadow. But before the abstraction, one more concrete telling of the whole lock and key story, in the oldest metaphor I have for it, a coil and a cut. Chapter 9. The Coil and the Cut. The last 2 chapters were exact, the Rabin function, the 4 roots, the greatest common divisor, the hinge. Exactness is where trust lives, and I would not trade it, but there is a cost to exactness. It can leave the feel of the thing behind. So let me tell the whole lock and key story once more, not with primes and remainders, but with a single image I keep coming back to when I want to feel, in my body, why a one-way function is shaped the way it is. The image is a coil and a cut. Imagine a long wire wound into a seamless coil, a spring, a spiral of many turns, wound so smoothly that the loops blur together into one continuous public loop. Anyone may hold it, anyone may turn it over, measure it, run a finger around its outside. There is nothing secret about the coil as a whole. It is out and then open, passed hand to hand. This is the public number, n, the thing everyone is given, the magnitude with nothing hidden on its face. But the coil was not wound from a single loop, it was wound from two separate coils, twined together so tightly that from outside they read as one seamless whole. Those 2 inner coils are the 2 primes, P and Q. They are still in there, wound through every turn, but you cannot see them from the outside. The winding has blended them into a single unbroken surface. The public coil is genuinely made of the 2 private ones, and just as genuinely gives no sign of where one ends and the other begins. Now, to open the coil, to recover a message locked inside it, or to reveal the 2 strands it was wound from, you must cut it, but not just anywhere. There is exactly one family of places where a cut does the right thing, where it separates the 2 twined coils cleanly instead of just mangling the wire, and knowing where those places are is the whole secret. Whoever wound the coil knows. They kept the 2 inner coils. They remember how the twining went. They can see, where no one else can, exactly where to lay the blades of the 2 strands fall apart intact. That knowledge is the trapdoor, the hinge from the last chapter, the memory of the 2 legs, the thing that stands the flattened figure back up. To the winder, the cut is obvious and instant. One motion and the coil opens into its 2 honest strands. To everyone else, the seamless coil offers no hint of where the cut goes. They can see the whole outer loop perfectly. Every turn of it is public, and it tells them nothing about the seam. They would have to try cut after cut after cut, testing places, hoping to stumble onto one of the rare right ones, and the number of wrong places to try is what runs away from them, exactly as the number of factors to test ran away in Chapter 2. The coil is open to the eye and closed to the hand, public in its shape, private in its seam. The public loop anyone can hold, the two private coils that alone reveal where to cut, and the product that never points back to its factors. This is the same asymmetry the whole book has been circling, told in wire. Winding the two coils into one, that is easy, that is multiplication, that is the walk downhill. You just twist them together and the seamless public loop appears. But going backward, finding the seam in a coil someone else wound, cutting it back into its two honest strands, that is the climb up the cliff, the wilderness with no map, the factoring wall. The winding forgets nothing. The two coils are still in there, but the seamless surface points nowhere. The product never points back to its factors. And notice what the cut is, in the language of the earlier chapters. The seam, the special family of places where the blade separates the strands, is the factor angle, the rare turn where the triangle's leg lands exactly on a divisor. The winder's knowledge of the seam is the hinge, the trapdoor, the kept memory of the two legs. The endless wrong places the outsider must test are all the other angles on the circle, the ones that give a legal triangle, but not a true split. The coil is the rig told as a physical object you could hold in your hand and turn in the light. The same lock, the same key, the same wall, in a metaphor with a heft to it. I offer the coil not as a new argument but as a place to rest before the hardest part of the book. We have now seen the lock and key story 3 times, arithmetically, as squaring and greatest common divisors, geometrically, as the bloom and the hinge, and physically, as the coil and the cut. They're one story, a public thing that anyone can hold, made from two private things that no one can read off it, openable by a single motion available only to whoever kept the secret, and sealed to everyone else behind a wall that stands exactly as tall as the gap between what a number is and what it is made of. Now we throw the strands away. In the next part we keep only the public coil, only the number n with its factors discarded, and we ask what it looks like from the outside, what the wall looks like to the one who was never given the seam. That is where the second prime becomes a shadow you can see but never stand on, and where the whole secret turns out to be a single missing angle on a circle anyone can draw. Part 4. The Shadow. Chapter 10. The Leg You Can Never Stand On. Until now we have always built the triangle the same way, 2 primes as the legs, their product as the area, the hypotenuse closing them off. The primes were the inputs, everything else followed. In this part we turn the construction inside out. We take the public number as our starting point and try to work backward to the primes, and in doing so we meet the strangest object in the whole book, a second prime that the figure can see but never stand on. It has earned its own symbol. I write it Q-breve, and this chapter is its portrait. Stand the rig a different way. Instead of making the 2 primes the legs, make the public number n the hypotenuse, the long side, the diagonal. Now swing the triangle, changing its angle, sweeping one leg down toward the axis, and watch for the moment when that leg lands exactly on a true factor of n, when it comes to rest at a whole prime p. You can do it. There is nothing stopping the leg from landing clean on p. The angle exists. The leg reaches it. One factor is caught exactly, sitting there as an honest whole number. But look what the other leg is forced to do at that instant. The triangle has a right angle. The 3 sides are bound together by the oldest relation in geometry. The square of the hypotenuse equals the sum of the squares of the legs. With the hypotenuse fixed at n and one leg pinned to the whole prime p, the second leg has no freedom left. It is forced to a specific length, and when you work out what that length must be, you find it is not the second prime q. It is p times a peculiar quantity, the square root of q squared minus 1. Q breve equals the square root of q squared minus 1. The second leg is forced to become p times q breve, and q breve is an irrational number that falls just short of the whole prime q and never quite reaches it. It deserves its mark, and the mark tells its story. I write it q breve, q with a breve, the little curved stroke that in the old pronunciation guides means short, because that is exactly what it is. The prime q shortened, not a different number wandering in from elsewhere, but q itself, fallen a hair short of whole, holding at the breadth of a breve. And it can never be whole. This is not a matter of not having looked hard enough. It is forced, and the forcing is beautifully simple. By its definition, q breve squared is exactly q squared minus 1. Q breve squared equals q squared minus 1. So if q breve were itself a whole number, we would have two perfect squares, q breve squared and q squared, differing by exactly 1. But no two perfect squares differ by 1, except 0 and 1 at the very bottom of the number line. The gaps between consecutive squares grow, 1, 4, 9, 16, and are already too wide to leave room for a difference of 1 anywhere above the start. So q breve is trapped forever between whole numbers, an irrational shadow that can approach q as closely as you like and never arrive. The rig can see the second prime. Q breve sits right there in the figure, 1 breve short of q, pointing straight at it, but it can never stand a leg on it. One factor caught, the other only shadowed. The rig can see the second prime. It sits right there in the figure, but can never stand a leg on it. One factor caught, the other only shadowed, held at the breadth of a breve. Now here is the part that turned this from a curiosity into something I think is genuinely deep. The triangle still closes. Despite the second leg being this short irrational thing, the figure is a perfect right triangle on n. The sides fit exactly, with no error, no gap. Watch how the exactness happens. P times q breve, squared, plus p squared, equals n squared. The long leg squared, plus the short leg squared, equals the hypotenuse squared, the ancient relation, satisfied exactly. And when you unfold why it works, you find a perfect cancellation. The long leg p times q breve, squared, carries inside it a buried minus 1, because q breve squared is q squared minus 1. That buried minus 1, multiplied by p squared, produces a shortfall of exactly p squared, and the other leg is exactly p, whose square is exactly p squared. The shortfall on one side, and the small leg on the other undo each other perfectly. The minus 1 hidden inside q breve and the little leg p squared cancel, and what is left is precisely n squared. That cancellation is the triangle closing. Sit with what that means, because it is the moral of the chapter and, in a way, of the whole book. The price of standing on one prime is a shortfall of exactly p squared in another leg. You wanted both factors as clean whole numbers. You got one, p, caught exactly, and the instant you pinned it, the other factor was pushed off the integers into irrationality, short by just enough that the figure still closes. The integer you gain on one side is the irrationality you owe on the other, and the two balance to n squared every single time. You cannot have both legs whole. The geometry will not let you. Reach out and make one factor a solid whole number to stand on, and the second factor becomes a shadow, present, visible, pointing right at the prime it shortens, but forever a breve away from being a place you could set your foot. This is the wall again, wearing its most vivid face yet. In Chapter 2, the two readings, magnitude and factorization, refuse to reduce to 1. Here we watch the refusal happen in a single figure, in real time, try to force both factors into the open as whole numbers, and one of them slips into irrationality to keep the triangle honest. The number will show you one prime or the other, but the act of grasping the first is the act of shadowing the second. Q breve is the shape of that refusal. The second prime, shortened, held always just out of reach. And if pinning one prime shadows the other, what happens when we pin neither? When we throw both factors away and keep only the public number n, then the triangle stops being a triangle at all. It opens into a circle. That is the next chapter, and it is where the whole secret comes to rest in a single withheld angle. Chapter 11. The Whole Secret in N alone. In the last chapter we kept one prime and watched the other fall into shadow. Now take away both. Keep only what anyone is actually given. The public number n, with its factors discarded, its two legs thrown away. Ask what the figure looks like now, built from the magnitude alone. The answer is the quietest and most complete statement of the wall in the whole book. From n alone, the triangle is not a triangle, it is a circle. Here is why. Once the factors are gone, the only relation you can still write down is the one that binds any right triangle on n. The two legs, call them a and b, must satisfy. A squared plus b squared equals n squared. The square of the hypotenuse, fixed at n, equaling the sum of the squares of the legs, but without the factors. Nothing pins a and b to particular values. Every angle you could swing the triangle to gives a different legal pair. Turn it a little and it grows while b shrinks. Turn it back and they trade. Each angle theta produces a perfectly valid right triangle on n, with one leg equal to n times the cosine of an angle and the other equal to n times the sine. A equals n times cosine theta, b equals n times sine theta. Every angle works, not one triangle, but a whole continuous family of them, one for each turn of the sweep, and the shape traced by the tip of a hypotenuse of fixed length n, swung through every possible angle, is exactly a circle, a quarter circle of radius n, every point on it a different legal split of the number. In terms of n alone, the triangle has dissolved into a circle, and each point on that circle is one possible way the number could come apart. In terms of n alone, the triangle is not a triangle at all. It is a circle, a quarter circle of radius n, every point on it a different possible split. The circle is public. Anyone can draw it. Given n, you know its radius exactly. You can sweep out every point. You can see the whole family of possible splits laid out in front of you. Nothing is hidden about the circle itself, and that is precisely the trap, because the circle shows you everything except the one thing you need. Somewhere on that circle, at one rare, specific angle, a leg lands exactly on a true divisor of n. That is the factorization, the special theta where the sweep passes through an honest split, where the leg comes to rest on a real factor rather than an irrational near miss. In the figures I drew for this I mark those special angles with red dots, the factor angles, the true splits, sitting on the public circle among the infinity of false ones. For a number like 15 there are only a couple of them, 2 red dots on the whole sweep, and every other point on the circle is a legal triangle that is not a factorization, a split into 2 numbers that do multiply to give the right area, but are not both whole, not both divisors, not the secret. And here is the wall, stated as plainly as I know how to state it. The circle points nowhere, nothing about it, not its radius, not its curve, not any feature you can read from n alone, singles out the red dots. They are not brighter. The circle does not bulge toward them or dip away from them. They sit among the false angles utterly unmarked, and the only way to find them is to swing and test, to try angle after angle, checking each one to see whether the leg has landed on a real divisor, and almost always finding that it has not. The public circle hands you every possible answer at once and refuses to tell you which ones are true. N gives you the circle. It withholds the angle. N hands you the circle and keeps the angle. The factors are there, one caught, one shadowed, but the turn that finds them is the secret. That single withheld angle on a circle anyone can draw is the whole of the wall. Everything this book has built, the triangle, the bloom, the hinge, the coil, the shadow prime cube reeve, comes to rest here. The magnitude gives you the circle freely, completely, with nothing held back about its shape. The factorization is one angle on that circle, present, real, sitting right there among the others. But the circle casts no light on which angle it is, and so the factors, though they are genuinely in the figure, are unreachable from the figure. And Q-breve, the shadow prime of the last chapter, is exactly what every non-factor angle produces, the second prime shortened. The near miss that the sweep keeps landing on instead of the truth Q-breve is the shadow every wrong angle casts. The red dot is the one right angle that casts none. This is the deepest still image in the book, and I want to let it stand before we move. Picture the two people who might hold this circle, the one who kept the two legs, the winder of the coil, the keeper of the hinge, knows the angle without swinging. The factorization was never hidden from them because they never threw it away, and the one who was given only ends sees the identical circle, complete and public, and cannot find the angle no matter how long they sweep, because the circle they hold is exactly the same circle and it points nowhere, same figure, same public radius. One knows the turn and one never will. The whole asymmetry of the modern world, everything in Chapter 1, is that difference, and it fits inside a single circle and a single missing angle. There is one more still image to add to this before Part 4 closes, the fold. If the circle is the wall seen as a withheld angle, the fold is the wall seen as a collapsed interior, a spiral wound flat until its inside vanishes, reopened only along the one line you folded it on. That is the next chapter, and it names the shape of a one-way function in the most tactile way the book offers. Chapter 12. The Fold and the Gyre. A secret is something with an interior. That sentence is the hinge of this chapter, and once you believe it, the shape of a one-way function becomes almost obvious. A thing with no inside can keep nothing. A line, as we said long ago, keeps no secret. To hide something you need an interior, a within, a folded-away space that the outside does not reveal. This chapter is about what happens to an interior when you flatten it, and about the one line that can ever open it again. Start with a spiral, a gyre, wound loosely, turn upon turn, with open space between the loops. Call that open space the interior. It is real. It has area. You could tuck something into it, thread a message through its windings, and the spiral would hold it in the space between its turns. A wound spiral is a thing with an inside. It can keep a secret. Now flatten it. Press the gyre down along a single line until all its loops collapse onto one another, until the open space between the turns is squeezed to nothing and the whole wound thing becomes a flat stack with no interior left. Where did the secret go? It did not leak out the edges. It did not evaporate. It was folded away, pressed into the collapse, hidden not by being carried off, but by having its interior crushed shut. The flattened gyre still contains everything the wound one did, but you cannot read it, because there is no longer any inside to read. The within has been folded flat against itself. This is the whole shape of a one-way function, and I find it the most tactile picture in the book. The flattening is easy. You just press, and the interior collapses, and the wound thing becomes flat. That is the walk downhill, the multiplication, the winding of the coil, the forming of the public number. Anyone can flatten. Flattening is what makes the thing public. A flat gyre has no inside, nothing sticking up, nothing that reveals where the loops used to be. You can hand it to anyone. Its very flatness is its publicness. But to reopen it, to unfold the gyre back into a wound spiral with its interior restored, its secret legible again, you need to know the one line you folded it along. Not any line. The line. The fold has a specific crease, a single axis along which the collapse happened, and only by reopening along exactly that crease do the loops lift back apart into their proper windings. Fold along the right line and the interior blooms open again. The secret restored. Try to pry it open anywhere else and you only tear the flat stack, mangling it, revealing nothing. The crease is the trapdoor. The fold line is the only thing that reopens what the fold closed. Flatten a wound spiral and the interior collapses, and the line you folded along is the only thing that reopens it. How a fold becomes the shape of a one-way function. By now you can hear the whole book echoing in this single image, and I want to make the echoes explicit, because the point of telling the story so many ways is that the ways turn out to be one way. The fold line is the hinge. It is the same crease that, in Chapter 8, stood the flattened triangle back up. The trapdoor motion, the swing that reopens the collapsed interior. The flattening is the winding of the coil from Chapter 9. The pressing of two strands into one seamless public loop. The lost interior is the withheld angle of Chapter 11. The factorization present in the figure, but unreadable from it, because a flattened gyre, like a public circle, contains its secret and points nowhere toward it. And the reason the outsider cannot find the fold line is the reason they cannot find the red dot angle or the coil seam. The flat public thing offers no hint of the one crease that would reopen it, and the crease is to try run away from them exactly as the factors did in Chapter 2. A secret is something with an interior. Multiplication flattens the interior. Factoring is the search for the fold line that would reopen it, and the wall is the fact that a flattened thing, however completely it contains its secret, shows nothing on its flat public face of the crease that would let it bloom back open. The interior is not gone, it is folded, and only the fold line unfolds it, and only the one who made the fold was ever given the line. That closes the shadow, Part 4, and with it the book still images. We have now seen the wall standing perfectly motionless in four forms. As the shadow prime cube reeve that can be seen but never stood on, as the public circle that hands you every split, but withholds the true angle, and here as the flattened gyre whose interior is folded away behind a single crease. In each, the secret is genuinely present and genuinely unreachable, and the reaching is the whole of the difficulty. But there has been a quiet assumption under all of it, that you could travel to a prime, sweep to an angle, walk to a factor, as though the prime sat in a landscape you could cross on foot. In the last part of the book that assumption breaks, and it breaks in the most interesting way of all. A prime, it turns out, is not a place you travel to. It is a leap, and once you see that, the whole rig stops being a thing that moves and becomes a deck of flat states you lay down and read across at a glance. That is where we end. Part 5. The Leap. Chapter 13. A prime is a leap, not a place. There has been an assumption hiding under every moving picture in this book, so natural that you never noticed it, and it is wrong. We have talked as if the rockets travel up the axis, climbing from prime to prime, crossing the distance between them, arriving. In this chapter that assumption breaks. To go from one prime to the next, taken literally, the rocket would have to cross an infinity, and it never could. So it does not travel, it leaps. And in that correction is the strangest and, I think, the truest way of seeing the whole thing. Here is the trouble, and it is old, older than cryptography, older than algebra. To travel from one prime to the next, the rocket must cross the stretch of the number line between them, but between any 2 points on that line lie infinitely many more, halfway, then halfway again, forever, an endless nesting of intermediate positions that never runs out. To cross the gap by traveling, the rocket will have to pass through every one of that infinity of points, in order, one after another. It would have to complete an infinite journey to move a finite distance. Taken literally, it never arrives. This is Zeno's ancient trap, the paradox of the runner who must first cover half the distance, then half the rest, and so can never reach the end, and it applies with full force to any rocket that tries to travel from prime to prime. So the rig does not travel. That was the mistake in the picture, and correcting it changes everything. The rocket does not crawl up the axis through the infinity of intermediate points. It leaps. Each prime is not a place the rocket walks to but the amplitude of an instant jump, a kick of a certain size, delivered whole, crossing no intermediate ground, because there is no traveling through the between at all. The prime is not a destination on a road. It is the size of a jump. You do not measure how far the rocket went. You measure how hard it kicked. This reframing has a consequence I want to state carefully, because it is the heart of the chapter. You measure the toll, not the road. The road between 2 primes is infinite, That is what Zeno showed. That is what makes traveling impossible. But the toll, the gap itself, the size of the jump, the amount of resistance you have to clear to get from one prime to the next, is perfectly finite. It is a definite number. This many steps of resistance but much of a kick. The infinite thing is the road, the continuum of points you would have to cross if you crawled. The finite thing is the toll, the amplitude of the leap, and what you pay. What the rig actually registers is the toll. You never traverse the infinite road, because you never travel at all. You simply pay the finite toll and appear on the far side. You measure the toll, not the road. The road between primes is infinite, the toll, the gap, the resistance, is finite, and that is what you pay. The rocket, then, does not move up the axis so much as tunnel. It appears at the next prime without ever having crossed the distance to it, the way a struck bell does not travel to its note, does not slide up through all the pitches in between, but simply rings, arriving at the tone hole and at once. The bell's note is not a place the sound walk to. It is an amplitude, a size, a kick of a particular magnitude delivered instantly. The prime is the bell's note. The rocket rings it. There is no journey to the pitch. There is only the striking, and then the tone. And here is the part that unsettles me pleasantly every time. If the rocket does not travel, if there is only the leap and never the crossing, then the motion between the ticks was never lost. It never existed. There was no smooth glide up the axis that we somehow failed to watch. There were only the kicks. Leap, 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 each one whole and instant, with nothing at all in between, because in between was the infinite road no one ever traveled. The continuity we imagined, the rocket sliding smoothly from 2 to 3 to 5, was a fiction we painted over a sequence of jumps. Strip the fiction and what remains is bare, a series of finite tolls paid, a series of bells rung, and no motion of any kind connecting them. The motion between the ticks is not lost. It never was. The road is infinite, the toll is finite, and the leap is free. Why does this belong in a book about the factoring wall? Because it recasts what the wall is made of, and it does so in a way that resolves an old discomfort. All along we have measured hardness as resistance, how hard a number is to pull apart, how much work the search costs, and resistance, in the light of this chapter, is exactly the right word, more literally than I first meant it. The difficulty of factoring is not a distance you have to travel, not a long road to the answer that we could shorten with a faster vehicle. It is a toll, an amount of resistance built into the structure, finite but real, that must be paid to make the leap from the public number to its factors. And the reason no faster vehicle helps is that there is no road to speed along. There was never a road. There is only the toll, and the toll is the wall, a finite resistance you cannot travel around, because the traveling was always an illusion. You measure the resistance, not the distance. The resistance is what the number charges, and it charges it whether or not anyone ever finds a way to pay. There is one last gift in the leaping picture, and it reshapes the whole rig. If each state of the machine is an instant leap with no depth, no duration, no road, if every flattened moment of the climb takes up no time at all, then the moments do not have to be lived through in sequence. They can be laid down side by side, all at once, a deck of flat instants read across in a single glance. That is the final chapter of the argument, and it turns the moving rig into something you do not watch but survey. We end there. Chapter 14. The deck of flat states. If a prime is a leap and not a place, if there is no road between the ticks, only the instant kick, then each state of the rig is a flat thing, taking up no depth of time, no stretch of travel, and flat things can be stacked. This short chapter is about the consequence of that stacking. The moving rig, which we have watched climb and breathe and bloom, can be laid out flat, every state of it side by side, and read across in a single glance. You do not move through the states. You lay them down, and look. Consider what one state of the rig actually is now that we understand the leap. It is a single flattened configuration, 2 legs at their current lengths, the triangle at its current posture, the bloom at its current symmetry, a complete still snapshot of the machine at 1 prime. And because the leap is instant, because that state was arrived at by a kick and not a crossing, it has no thickness in time. It is genuinely flat, a two-dimensional slice, a card. Now here is the simple, strong observation. A flat card takes up no depth, so you can set another flat card behind it, and another behind that. Infinitely many. A deck of them. Every semi-prime, every setting of the rockets, every moment of the climb, standing side by side in a third dimension that the flat states themselves never used. The rig was two-dimensional. Its states live in a plane. That leaves the entire third dimension free, unused, available, and into it you can stack the whole history and future of the machine at once. Every state the rig could ever be in, laid down in a deck, readable across in one look. Because each rig, flattened, takes up no depth, you can stand infinitely many of them side by side. A deck of flat states, read across in a single glance. There is a quiet symmetry here that I find almost too neat, and it is the payoff of the whole part. The same flatness that makes the wall strong is the flatness that lets you build the deck. Recall why the wall is strong. The public number is flat. The gyre was pressed down until its interior collapsed. The coil was wound until its seam vanished. The triangle was flattened until its legs folded away. Flatness is what makes a thing public and secret at once. Public because there is nothing sticking up to read. Secret because the interior has been pressed shut. The flatness is the wall, and that same flatness, the very property that hides the secret in any one state, is what frees the third dimension to hold all the states together. Because each card is flat, the cards stack. Because the secret is folded into two dimensions, the third is left open for the deck. The wall's strength and the deck's possibility are the same flatness, seen from two sides. So you get a strange kind of overview without ever getting the secret. You can lay out every state of the rig and read across them. Compare the semi-prime to that one. Watch the blooms go round and thin across the whole deck. Survey the entire landscape of difficulty in a single glance. The comparison is free. The third dimension was always available for it. What you cannot do is use the deck to reach into any one card and pull out its folded secret. The overview is total and the secret is still sealed. You can see all the walls at once and climb none of them. Reading across the deck tells you everything about the shape of the difficulty and nothing about how to defeat it, which is, in the end, exactly what this whole book has been. A way to see all the walls at once, laid flat and read across, without pretending that seating them is scaling them. You do not move through the states. That is the sentence to end on. We began the rig as a thing in motion, rockets climbing, triangles breathing, the whole machine pulsing in the jagged meter of the prime gaps, and we end it as a thing at rest, or rather beyond motion, a deck of flat instants laid down all at once, surveyed rather than traveled, because the motion between them was the illusion we cleared away in the last chapter. There was never a climb. There were only the states, and now they lie in a deck, and you look. That is the last of the seeing. One task remains, the honest accounting the whole book has been promising since its first pages. Every construction here was built, in part, to test whether some shape could reach through the wall and read a number's factors off its public face. None did. The final chapter is the reckoning of that, where every one of these beautiful machines stores what you fed it and forges nothing, and why no shape reaches the wall. It is the null result the book was always walking toward, and it is where we close. Chapter 15. Storage and the Forge. Here is the accounting the whole book has been walking toward, and it is a confession as much as a conclusion. Every construction in these pages, the rig, the bloom, the hinge, the coil, the shadow prime cube reeve, the public circle, the flattened gyre, the deck, was built, somewhere in its motive, to test a hope that some shape, some clever geometry, might reach through the wall and read a number's factors off its public face. This is the record of that test, and the result is a null one, stated plainly. No shape reaches the wall. Every construction stores what you feed it and forges nothing you don't. Let me name the distinction the chapter turns on, because it is the whole of the matter. Storage versus forging. To store is to hold what you were given. If I hand a construction the two primes and it builds a beautiful triangle whose legs are those primes, it has stored them. It is showing me, in geometric form, exactly the information I fed in. That is honest and useful. But it breaches nothing. I already knew the primes, or I could not have built the figure. To forge would be something else entirely. To hand a construction only the public number n, and have it produce the factors that were never given. To manufacture the secret from the public face alone. Storage is showing you what you put in. Forging is minting what you did not. The wall is the claim that these geometries can store but never forge. And when I go back through every construction in this book with that distinction in hand, they all fall on the same side. Every one stores, not one forges. Every geometric construction built to read a number's factors stores what you feed it and forges nothing you don't. Why no shape breaches the wall. Walk the accounting with me, construction by construction, because the honesty is in the specifics. The rig, with its two prime legs, you had to give it the two primes to build it. It stores them beautifully, it shows you their balance, their difficulty, their bloom. It forges nothing. Hand it only in and it cannot tell you the legs. The hinge that stands the flattened triangle up. It works only if you kept the two legs, only if you already hold the secret. It reopens what you folded. It cannot find the fold line of a gyre someone else flattened. It stores the trapdoor you were given. It forges no trapdoor you weren't. The shadow prime cube reeve. It lets you see the second prime once you have pinned the first. But pinning the first means already knowing it. And cube reeve itself is irrational, never a whole number you could read off and use. It shows you a shadow, it hands you no factor. And the public circle of chapter 11, the sharpest test of all, hands you every possible split at once and refuses to mark the true one. It is pure storage of the number n and pure refusal to forge the angle. The red dots are there, the circle points at none of them. Every construction, the same verdict. Give it the secret and it will store the secret gorgeously, in triangles and blooms and folds. Give it only the public face and it forges nothing. It hands back the circle, the shadow, the flat card, and keeps the angle sealed. The geometry is honest to a fault. It never manufactures what it was not given. And factoring is precisely the demand that something be manufactured from the public face alone. So no shape in this book breaches the wall. And I have come to believe no shape can, for the same reason. A construction can only fold and unfold the information it holds, and the public number simply does not hold, on its readable face, the angle that splits it. I want to be clear that this is a victory, not a defeat, and clear about why, because a reader who came hoping I would crack the wall might feel let down, and that feeling would be a misreading of the whole enterprise. I said at the very beginning that an honest null result is worth more than 100 overclaims, because it tells you something true about the wall's shape. This is that null result, and here is what it tells us. If the wall were an accident, a difficulty born of our not yet being clever enough, then you might expect that a sufficiently beautiful reframing, a clever enough change of shape, would dissolve it, the way the right diagram sometimes makes a hard problem suddenly easy. We tried that. We tried it many ways, with real care, following the geometry as far as it would honestly go. And the wall did not dissolve. It reappeared, intact, in every single construction, as the withheld angle, the irrational shadow, the vanished seam, the folded interior. A difficulty that survives that many honest reframings, that reconstitutes itself identically from every new angle, is behaving less like an accident and more like a structural feature. Every failed attempt to forge is a successful measurement of how deep the storage-only limit goes. The consistency of the failure is the evidence. That is the closest thing to a thesis this book can honestly offer. Not a proof that factoring is hard. I have no such proof, and I have told you so at every turn, but a demonstration, built up from physical pictures and carried out in the open with its dead ends kept honestly beside its results, that the difficulty is not a surface accident waiting for a clever shape to dissolve it. It lives deeper than any reframing reaches. A number's magnitude and its factors are two readings that never reduce to one, and every construction that tries to reduce them ends by storing the one it was given and shadowing the other, which is exactly what the wall would look like, if the wall were real. So we end where we began, at the wall, but no longer leaning on it blindly. We have walked its whole length now. We have seen it stand at exactly 2 factors, felt its difficulty in the posture of a triangle, watched it become a real lock at the rapid hinge, followed it into the shadow of Q-breve and the withheld angle of the public circle, and understood at last that a prime is not a place you travel to but a leap you take, and that all the walls can be laid flat and read across at once without a single one of them being scaled. The secret was never the number. It was always the 2 legs, and the hinge that remembers them, and for everyone who was not given the legs, the number hands over a circle, complete and public and beautiful, and keeps the angle. That kept angle, on a circle anyone can draw, is the whole of the wall. I cannot prove it will stand forever, but I have shown you its shape, honestly, from every side I could find, and its shape is the shape of something built into the numbers, not laid over them. That was all I ever hoped to do, not to break the wall, but to let you see it clearly enough that its standing stops feeling like luck and starts feeling like law. End. Colophon. On the sources. This book grew out of 2 working notebooks kept in the open. rsacrack.com gathers the essays and research on the geometry of factoring, the wall at 2, the fold and the gyre, the coil and the cot, the prime helix construction, and the honest record of constructions that store, but do not forge. ONOJK123.com hosts the rig itself, the moving picture of 2 prime rockets climbing the axes, the semi-prime scanner, the rapid hinge, the shadow prime Q-breve, the public circle, and the leap. Both are the work of Jonathan Kendall in San Diego, and both remain what they were, notebooks on factoring, kept in the open, honest about where they touch real cryptography and where they are only a beautiful way to think. Nothing here is a proof, and nothing here is a cipher. It is a way of seeing, built from physical pictures before reaching for abstraction, and preferring an honest null result over an overclaim. The Wallet 2, First Edition, 2026. Companion volume to rsacrack.com and onojk123.com. github.com/onojk